Chapter 12, Part 2, on Intermolecular Forces. Intermolecular forces are those forces of attraction that exist between molecules. The three types of intermolecular forces are, in order of increasing strength, first, least strong, dispersion, dipole-dipole, and then hydrogen bonding. The strong intermolecular forces tend to result in liquids and solids with high melting points and boiling points, where the weak intermolecular forces tend to result in low melting points and boiling points. First, the dispersion forces. This is the default intermolecular force. It's present in all molecules and atoms. It's the dispersion force and is also called the London force. Dispersion forces are caused by fluctuations in the electron distribution within the molecules or atoms. They're momentary dipoles. For example, here's a helium with its electrons symmetry apart, but in this case we see this part of the molecule, the electrons are going to create a kind of a negative part here and a positive part there. It's like an induced dipole. The dispersion force is the instantaneous dipole of any one of the helium atoms, and that it attracts the neighbor. So what we see is this partially negative gets attracted. There's an force of attraction between this helium and that, and because of the induced dipole. They're very weak attractions. The dispersion forces, the size depends upon how easily the electrons in the atom can be polarized. A larger electron cloud results in a dispersion force that's a little stronger because the electrons are held less tightly and can be polarized. Iodine is an example of a pretty large molecule which is highly polarizable. The solid state of iodine has only weak dispersion forces holding it together. They're looking like that. The effect of differences in dispersion forces on gases. Now let's remember that increasing the boiling point means they're held more tightly with stronger forces, because to boil you have to break those forces so that the molecules can escape as a gas. And we notice that helium, the lightest gas, boils at a fairly low temperature, and as you get heavier gases they boil at heavier. That's because the dispersion forces in the larger, more polarizable clouds create a little bit stronger dispersion forces. So as the size of the molecule, of a nonpolar molecule, increases, it becomes more polarizable. The second kind of force is called the dipole-dipole force, sometimes called the van der Waals force. But the dipole exists in all polar molecules. Polar molecules have permanent dipoles, and so they interact with these dipoles with their neighboring atoms. Formaldehyde is a polar molecule. The oxygen part is kind of negative, it pulls the electrons toward it, and this part is kind of positive. It looks like this, partially negative, partially positive. And what happens in the dipole-dipole intermolecular bond is that the negative part of one molecule is attracted to the positive part. And you can see this. This is a stronger force than the weak dispersion London forces. Here's how that affects. Again, using boiling point. Formaldehyde has dipole-dipole forces, and it boils at minus 19 degrees Celsius. Ethane, which is a nonpolar molecule, has only dispersion London forces. It boils at minus 88. So very weak, a bit stronger. Miscibility, a liquid's ability to mix with another liquid without separating into two phases. You see pentane, these are the pentane molecules, they're nonpolar, and water molecules, they do not mix. The pentane stays on top. We see oil and water, In a salad, oil and vinegar in a salad dressing, they don't mix. And there's an oil spill that doesn't really mix with seawater. A molecule has a dipole forces if it's polar. So remember, you need to know if a molecule is polar. In order to do this, you have to look at its Lewis structure, determine the geometry, determine if the molecule contains polar bonds, that is, atoms that have difference in electronegativity, determine whether the polar bonds add together to form a net dipole moment. Chloroform. It's a perfect tetrahedron. However, chlorine is more electronegative and it pulls the electrons toward it, so there'll be a sort of a negative part of the molecule as opposed to the positive. Water also has again the negative part that's on the oxygen and the positive part here. These are both polar molecules, and they will interact with each other in water in solutions by dipole-dipole forces. The strongest of all is the hydrogen bond. And note that polar molecules that contain hydrogen atoms bonded to fluorine, oxygen, and nitrogen. Not that any other negative nonmetal, just fluorine, oxygen, and nitrogen. They exhibit a property called intermolecular force called hydrogen bond. Here's HF. This is, of course, has a permanent dipole. And here is this strong bond of the hydrogen being attracted to the fluorine. In the hydrogen HF, the molecule on each side is strongly attracted to the fluorine of its neighbor. And this is the hydrogen bond, the strongest of all intermolecular bonding forces. Here we take a look at hydrogen bonding in water. The hydrogen, which is attached to an oxygen, is strongly attracted to the oxygen in another molecule. Again, in methanol, the hydrogen, which is attached to oxygen, is strongly attracted by hydrogen bonding to the oxygen in another molecule. How strong is this effect? Well, let's take a look at methanol, which of course has hydrogen bonding. It boils to 64.7 degrees Celsius, while ethane is nonpolar and has only dispersion forces, and it boils at minus 88. So the strong intermolecular bonding of hydrogen bonding shows that it's very strong. Hydrogen bonding in water. Here's a picture of what it looks like. Water is a fairly light molar mass. It's only 18.02 grams per mole. It should almost be a gas, but because of the strong hydrogen bonding, we find water in the liquid state. Table 12.5 summarizes different types of intermolecular forces. Dispersion forces are present in all molecules and atoms, and it increases with increasing molar mass. So here we have hydrogen, only dispersion. Here we have only polar molecules like HCl, hydrogen chloride. And then we have the hydrogen bond because we have hydrogen bonded to fluorine. There's also hydrogen bonding in DNA. You might not recognize it, but here's how the bases on the cross steps of the ladder bond by hydrogen bonding.